You could imagine Einstein, I mean, we can play this little game. Einstein goes to his physics teacher with this electromagnetic problem. He says, look, physics teacher, if I hold the coil and move the magnet, I get this current. If I hold the magnet and move the coil, I get the same current. What's the difference? Why is it so different? That teacher could have said to young Einstein, Einstein, shut up and calculate, right?
Yeah.
Use Maxwell's equations. Yeah, you'll use them differently in the two cases. You'll get the right result both times. Shut up. Stop worrying about what's really going on. And then we would have never had relativity. We have it because he wouldn't shut up, because he was trying to think it through. Yeah, I think that is absolutely the mark of great physics, to try to get clear about really what you're postulating. And that requires conceptual clarity. It requires clarity in argumentation, all of the things that make for a good philosopher.
Einstein's theories of special and general relativity totally changed physics, and they had a huge impact on philosophy as well. And it's been over 100 years, and people, as you know very well, much better than me, are still grappling with their implications, still confused by key tenets of the theories. So that's one thing. The other thing, as you know, I've been doing some more pedagogically oriented episodes focused on topics in philosophy and physics. So I most recently talked to David about the measurement problem. We did another episode on times arrow. I just talked to Barry Lower for our listeners on the philosophy of science. But I thought that you were precisely the person to talk to about special and general relativity. So with all that said, I wanted to start off by asking, what was the context in physics before special relativity that led or formed the furnace out of which, or maybe the crucible is the right word, out of which special and general relativity arose?
Couple historical things to understand, because the question you ask sounds perfectly reasonable and is perfectly reasonable as a question.
Thanks.
But the answer isn't the kind you're looking for. And this is part of why there's a lot of misunderstanding about both those theories, really. The crucible from which special relativity came was the inside of Einstein's brain.
Okay.
It wasn't, I mean, remember how young he was, right? He was he was a patent office clerk, 1905. He was not steeped in the whole, milieu of theoretical physics for a long time. And when you look at 1905, the so-called Annus Mirabilis, right? He's writing the paper that essentially proved that there are atoms, which was on Brownian motion. He writes the paper that basically kicks off quantum theory as we now understand it. I mean, there was Planck stuff before, but he has a paper on the photoelectric effect that is really the beginning of quantum mechanics. He writes on the electrodynamics of moving bodies, which is what we would call the special relativity paper. He writes another paper following that, E equals mc squared, okay? And this guy's in his 20s. What have you done recently? Okay, so what do we know? We know he had this amazingly fertile mind for physics. And the fertility came from a certain desire for conceptual clarity and thinking about, I mean, you can call them thought experiments, but it's a little misleading to call them thought experiments. Thinking about the implications of physics in very simplified situations, right, where a lot of the detail washes away. I mean, Einstein always talks about in his autobiography, even when he was a teen and he first learned about electromagnetic theory, Maxwellian electromagnetic theory, and the idea that light is electromagnetic waves. And then he asked himself the question, which, if you understand that theory the way Maxwell did, seems like a kind of reasonable question. What if I were traveling along with an electromagnetic wave? what would it look like, as it were? Or, I mean, that's how it looks is, of course, kind of metaphorical. But in the same way that you would ask about a water wave, I mean, imagine a wave in the ocean. You think, well, waves in the ocean, here's something that never happens, that can't happen, that there's a lump in the ocean and it just sits there, right? I mean, a wave travels.
Yeah.
And you can't, if you try to pile up the water to make a wave and let it go, it'll just, it won't do it. It'll just disappear. On the other hand, if you imagine a water wave moving this way, and you happen to be above it moving at the same speed, and you look down, you would see a lump of water just sitting there, right?
Mm-hmm.
You'd be a little surprised about that. And you'd say, what's going on? And you could finally work out, oh, I see, I'm kind of moving along with it. Now, Einstein said he exactly asked himself this question about electromagnetic waves. What if there's an electromagnetic wave and I'm traveling at its speed, or describing it, if you will, from the point of view of a frame of reference that's moving at its speed? Then it wouldn't be moving in that frame of reference. But then you're supposed to have this electric field and this magnetic field at right angles. They're in a certain state, and they're not doing anything. And he said, but there's no way to describe that using Maxwell's theory. He said something like, we never see anything like this, these sort of static electromagnetic bumps, if you will. That's something that bothered him as a teen. There's a historical error here that everybody repeats, and I'll tell you the little story about, we think, why people say this. So it became a standard thing to say, oh, the great ferment over electromagnetic theory was the Michelson-Morley experiment, because they'd been looking for evidence of this electromagnetic ether. I mean, just again, to walk back a second, you have Maxwellian electromagnetic theory that postulates these new objects, new physical ontology that they called fields. There's nothing like that in Newton. Electric field, magnetic field. Maxwell writes down some equations. And again, you have to remember a little bit, if you've learned this stuff in school, when we present Maxwellian electrodynamics, it's usually with like 4 equations. What Maxwell wrote down was 20 equations. And so Maxwell has these ideas, and there's kind of a lot of mixture of all sorts of different physical problems, and he kind of has this whole pile of ideas. Later, Heaviside reduces all of this to this kind of much cleaner presentation where there are only 4 equations, which is normally the way we learn it now. Einstein had the benefit of that simplification. So in a way, he learned a simplified version, if you will, or cleaned up version of Maxwellian electrodynamics, which meant that, again, with his kind of mind, he could think, what would happen in this situation? What would happen in that situation? Anyway, people were puzzled at the end of the 19th century about these fields. What were they? Because they weren't like anything Newton had. And they're defined everywhere. Unlike particles, which are always somewhere, fields are always everywhere. And there was this, it wasn't an empirical problem. It wasn't that Maxwell's equations were making bad predictions, but people were just puzzled. What are we even talking about? And there was this idea we need a mechanical model of the ether. So you imagine that, well, really there's some medium, like to have water waves, you gotta have water, right? It's a wave in what? In water. So people thought there must be a material medium, and then there's maybe stresses and strains in it, or somehow vibrations in it, or something like this. And so this thing was called the luminiferous ether. Luminiferous, to remind you of your Greek, just means literally light-bearing, right?
Mm-hmm. Fair.
Yeah, ferro is to bear, and lumen. So the luminiferous ether was supposed to be this mechanical, physical, material medium that these electromagnetic waves were waves in. And especially the British scientists really wanted to build a mechanical model. That is, you just use Newtonian mechanics, and you've got pulleys and gears and springs and God knows what. And you just, in your mind, I mean, it wasn't exactly serious physically, but just to make sense of it, can we build a mechanical model of the ether? They couldn't, because it had to have funny properties, right? For example, the tagline of Alien is, of course, in space, nobody can hear you scream. But they can see you scream, right? Why? I mean, we can't hear the sun. Why? Because there's no air between here and there, so you can't have sound waves reaching us from the sun. But we can see it. We can see the stars. We can see these. That means if these are waves, and they're waves in a medium, the medium has to stretch. It has to be everywhere.
Yeah.
And so if you, in your mind, you're thinking, oh, this is kind of like sound waves or water waves. But it has this other kind of medium that these are waves in. But furthermore, here's the Earth orbiting, and somehow it orbits through this thing and doesn't get slowed down. There's no friction that you can see, right? I mean, you would expect if there was a medium and things were moving through it, there would be the normal effects of a medium. So there was that problem. Now, everybody knew that was a kind of theoretical problem. Again, that wasn't an empirical problem per se. But one idea was, if you just start where I was at, you say, well, gee, the Earth is orbiting, and there's no friction. Somehow it's able to go right through this medium. The way, I mean, people would often say, as if the matter the Earth is made out of was like a net with big holes in it, and the ether was so fine it could just kind of pass through without dragging it. That gave rise to the idea that there would be an ether wind. That is, as the Earth spins and also orbits, somehow if you could see the ether, you'd see we were moving through it at different rates. And then
dragging it?
Well, no, we on this theory, we're not dragging it with us. That's why there's a wind, right? And that was the basis of the Michelson-Morley experiment. It was looking for evidence of this ether wind. And they didn't find it. It was a beautiful experiment, a lovely experiment to describe, highly, highly, highly sensitive to tiny little changes in the apparent speed of light without measuring the speed of light. I mean, it's a nice, again, conceptual thing that you can check for small differences in the speed of light without measuring the speed of light. Anyway, they didn't find that, so the ether wind theory looked like it was in trouble, but no, people didn't give up. Then there was, to use the phrase you just used, then they said, well, it must be that the Earth is dragging the ether along with it, entraining it, right?
The reason I thought it might have been a wind is I just imagine if we're dragging something, then if you're on the poles, if we're moving in the north direction, if you're on the east-west side of the Earth, you'd be feeling the ether dragging past you as if it were a wind. That's just what was going on in my...
Yeah. I mean, there's a question about you ought to be able to be in relative motion with respect to the medium, and then things would look different. Just as if you're in relative, I mean, think about the water wave case. The water wave is moving along, and it really is, as it were, moving with respect to the water, to the rest frame of the water. Right? You say, or take the speed of sound, right? So sound has a characteristic speed Mach 1 in air at standard temperature and pressure. Well, what's that speed relative to? What do you mean it has a speed? The answer is it's relative to the rest frame of the air. And there was a joke, I always tell this, I remember this, I thought it was funny when I was young on the show Laugh-In. They had a funny little joke because it was the time when the supersonic planes just started, the Concorde, right? So you could book a flight and go faster than the speed of sound. And they had a sketch where it's supposed to be the first flight of the Concorde, and you see all the people sitting in rows. And in the front row, one person turns to the other and says something, and then the next row back they answer, and then the next row back they answer, because, gee, we're going faster than sound. And it was funny, and then you say, but that's not right. It wouldn't be like that. Why? Because you're dragging there, you're entraining the air, right? There's still, speed of sound is still Mach 1 in the plane, but relative to the rest frame of the air that's in the plane. So everything would seem normal, right? Mm-hmm. So there was an ether drag theory that said, oh, that's why we're not seeing these differences in the speed of light in different directions on the Earth because the ether is being dragged along with the Earth. So that would solve that problem. But of course, you solve one problem, you bring up another problem. Then you have to think, okay, I've got this ether, it's going along with the Earth. The ether outside the Earth isn't being dragged. So there's going to be these layers where there's the transition between the dragged ether and the non-dragged ether. And that should have optical effects. So you look for stellar aberration. You look at the star, you would think, oh, the apparent positions of stars will be different when they go through this kind of intermediate layer. They look for that, they didn't find it. And so the other thing is, if you have in your mind, especially sound waves as your model for these electromagnetic waves, sound waves are pressure waves, and the variation is in the direction of motion. So it's like the sound wave is going this way, and you'll see this variation of dense, less dense, dense, less dense, and you think about how that works, and it propagates along. But electromagnetic waves, the variations in the electric and magnetic fields were at right angles. They're called transverse waves. So the electromagnetic wave is moving this way, and the electric and magnetic fields are, as it were, vibrating off in orthogonal directions in the usual way you present this. And so there was a question, well, what kind of medium can do that? We understand the kind of medium like air. Water waves are really complicated because actually the water, even though the wave is doing this, the water's doing this, and it's actually doing little circles. I mean, it's a complicated story about water waves. But the waves they knew about and the media they knew about had different features than these electromagnetic waves. So this was, I wouldn't say a crisis. It's just the kind of thing that if you're curious, you're saying, that's interesting. I mean, I wonder how that works, right? I mean, it was just a puzzle. And that was the kind of thing Einstein was trying to get a clear picture in his head of electromagnetic theory. Anyway, Michelson-Morley do this experiment. Sorry, Michelson-Morley, I think I learned from you it was Michelson. Michelson-Morley do this experiment, and they get a null result. They don't notice any apparent changes in the speed of light. And the normal story is that's what was really bothering Einstein, was explaining the outcome of that experiment. It was driven from that experiment. That's untrue. Now, there's been a little bit of a change. When I was in graduate school, the historians were saying, we don't even know he'd ever heard about the experiment. I said that on another podcast, and then someone said, well, there's new evidence that he had heard of it anyway.
Glad somebody's working on the history of this so intently.
Yeah. But whatever that's true, if you just have to read the paper, the 1905 paper, to see that wasn't the issue for Einstein. That's, to me, is what's really interesting that most people don't understand. Because you just read the first paragraph, it's wonderfully clear. And the title of the paper is on the electrodynamics of moving bodies. So you're talking about electromagnetic theory, and especially when you've got charged or magnetic bodies that are in motion, and in motion with respect to each other. So here's the actual situation Einstein describes in great detail at the beginning of that paper. So this is what he was thinking about, according to him at the time. If I take a coil of wire, like copper wire, wrap it around and around and around, and then hook it up to an ammeter, which measures current, okay? And I now have a regular bar magnet, right, with a north and a south side. Here's an experiment you can do. It's very easy, and this is predicted by Maxwell's theory. Take the magnet and push it through the coil. And if you do that, you'll see a little bump that there'll be some current that will be induced. So this is induced electrical current. When you go this way, the current goes one direction. When you pull it the other way, the current goes the other direction. If you stick the magnet right in the middle and put it on a spindle and spin it, the current will go both ways, and now you have something that produces alternating current. And if you connect that up to a hydroelectric dam, I mean a dam with water going through, and use the water to spin this thing, you now have a hydroelectric power plant. So the normal way you talk about that is you say, that's because the magnetic field is changing. As I move the magnet through, the magnetic field around the coil changes, and by Maxwell's equation, a changing magnetic field induces an electric field. So that creates an electric field out here. And the electric field points, using the right-hand rule, the electric field points around, and sitting inside the wire, you've got all these nice free electrons, and they're affected by that electric field, and they're driven around, and that creates a current, right? Nice story. If I do it this way, it creates an electric field in the other direction, drives them around the other way. That's fine. Now Einstein says, now let's do a different experiment, or let me put it this way. According to this theory is a different experiment. I'm not going to move the magnet. I'm just going to let the magnet sit here. I'm going to move the coil.
Really? That's a different experiment.
Yeah.
Okay.
Why? And this is if you just read the first paragraph of the paper, this is what Einstein's going on about. So I just hold the magnet and move the coil with the same relative speed. Well, now, because the magnet isn't moving, the magnetic field isn't changing. Because the magnetic field isn't changing, there is no electric field, right? Well, if there's no electric field, why are you getting a current? Well, because there's this other thing called the electromagnetic force, and this is, comes from another piece of Maxwell's equations. And it says if you have a charged particle moving through a magnetic field, that directly creates a force on the particle, not by creating an electric field, but directly creates a force on the particle. And that force is just exactly enough, as you might imagine, to create exactly the same current. And if you do it this way, so they're both moving, then you've got kind of half the electric field and half the electromotive force, but they add up to the same thing. And you get exactly the same phenomenon, right? Now, that is, in fact, what happens. So this is not, we did an experiment and it didn't come out the way we expected. What bothered Einstein was that the phenomena displayed a symmetry that the theoretical explanation didn't, right? The phenomena say, all I care about is the relative speeds of the coil and the magnet. Give me that and I'll tell you what the current will be. You don't have to specify this is moving and that's at rest, or this is rest, or they're both moving, or whatever. But the theory said it makes all the difference in the world. And Einstein said it. He said, when you move the magnet, according to the theory, you create this electric field. And the electric field even has an energy. So you'd have to say there's kind of energy content that's created out here. But if I hold the magnet and move the coil, I don't create an electric field. No energy created. So what bothered Einstein, and this makes sense for, again, this is a really smart guy who's just learned these theories and is trying to think them through and understand them. And he says, that doesn't seem right. If the phenomena are the same, shouldn't the explanation really be the same? Shouldn't the physical account of it? It's not impossible that two very different physical situations, theoretically described, create the same phenomena. That could happen. But he didn't like that. And so this is what was motivating him. It was a conceptual puzzle. You could say an aesthetic puzzle at a certain level, or the idea that certain kinds of explanations, right? Again, the basic principle is symmetries in the phenomena ought to be mirrored by the same symmetries in the theoretical explanation. So that's what really bothered him. And that's why the theory was called On the Electrodynamics of Moving Bodies. Now, if you read the paper, which it's not an intrinsically hard paper, but it's written in a very clunky way. As everybody said, Einstein actually wasn't a great mathematician. Everything's done in coordinate form and blah, blah, blah. And it on the face of it, it doesn't present itself as a revolutionary theory about the structure of space and time exactly. And the title of it, again, nothing about relativity, On the Electrodynamics of Moving Bodies. You can see why. That's the example. I've got some moving bodies and they have electric and magnetic fields. His math teacher, Minkowski, reads the paper, and Minkowski understands how to represent the paper, as it were, in terms of space-time geometry. And that's why we call it Minkowski space-time and not Einstein space-time. And it actually takes a little while for Einstein to accept this, because that wasn't how he was thinking about it. But eventually he comes around and says, oh yeah, really what I'm doing is postulating a different space-time structure. Now, all of this is overlaid by yet another confusion, which is that there had been another desire, which is associated with Mach, same Mach 1 guy, to say, oh, I want a completely relational theory. I want the theory to be presented in terms of purely relative quantities. That the only way of talking about motion is as the relative motion of two things. And again, to just stop for a second conceptually, Newton postulated an absolute space and time that has enough structure that you say, even if there's only one particle, and it's a vacuum, right? I don't have a medium, I don't have anything else. I just have bare space and time, empty space and time, right? Like Democritus, the empty, right? Nothing in it. And I have a single particle. In Newton's theory about the structure of space and time, that particle will always have a definite speed, definitely have a velocity, right? It could be at absolute rest, or it could be moving in any direction at any speed. And that is not the relative motion of that particle with respect to another material object, because there is no other material object, right? Mach didn't like that, because space and time, again, the background is a kind of empiricism. Space and time themselves are not directly observable. So if you restrict yourself to talking about what you can observe, you can't talk about empty space and time, right? They're unobservable. You can't see them, you can't touch them, you know. So Mach didn't like that. So Mach's out there saying, we can't do this. We somehow, again, just for these conceptual reasons, we have to reformulate physics only in terms of these relational quantities between matter, pieces of matter. Einstein says he wanted a Machian theory. He was convinced when he was young that the right way to go was to go with Mach, and the way to make progress was to reformulate the physics. Whether it made any difference to the predictions or not wouldn't matter, because again, you're solving a conceptual problem, if you will. Reformulate the physics only in terms of these relational quantities, relative quantities between pieces of matter. And he says early on that's what he wanted. Now, especially we'll get in a while to general relativity. When he set out to general relativity, he had that as a constraint. I want a Machian theory. So that was really what Einstein wanted. He wanted a theory where the phenomena, the symmetries in the phenomena were symmetries in the theoretical explanation, certainly. And he wanted a Machian, at the end of the day, he wanted a Machian theory where the only physical quantities having to do with motion were relative motions between bodies. Now, Newton had already argued quite effectively, and I don't know of any place where Einstein talks about this. Newton had come up with exactly this debate, and it happened with Leibniz, right? And it happened in the form of this set of letters indirectly between Leibniz and Clarke, Clarke was Newton's representative, the so-called Leibniz-Clarke correspondence, right at the end of Leibniz's life. And it was all about this. It was, is space in itself a thing that exists, that has a structure, or is all there is to space the relative positions of material bodies? And Newton was very clearly on the side of space and time are real entities, and they have a structure that's there independently of whether there's any material at all. And Leibniz, if you know Leibniz didn't like that. I mean, this is this kind of intermediate Leibniz. That is, the deep Leibniz is the monadology. That's just a kind of really crazy view. And then there's this sort of intermediate Leibniz where you're doing what looks more like recognizable physics. But one of Leibniz's ideas is that space and time and motion had to be exposited or understood as always the relative motions of bodies in some sense. There's no absolute motion. We just said for Newton, there's absolute motion. Even if there's only one material body, it can be moving. Now, that debate was really settled in a way by Newton in Principia with the bucket experiment. So maybe people know about this. I often say this could be, you could argue, was the single most important experiment in the history of physics.
Really?
Yeah. I mean, I would say it's between that and or you could say, if we get to general relativity, it was Galileo's experiment dropping a heavy and a light ball off of a building and finding that they fall together, okay? But the one, I think the most important experiment, because here you have this big debate that looks like a philosophical debate or metaphysical debate or something like that. What is the fundamental nature of space and time? So you have questions like, is the following thing metaphysically possible, that you annihilate all the matter but space and time still remain? And if you think space and time are nothing but relations between matter, the answer is no. You get rid of the matter, then there are no relations between matter, then space and time themselves are gone. And Newton, from the beginning in his scholium on space and time, is very carefully and beautifully arguing, no, space and time, absolute space and time exist. They're different in everyday life, we don't talk about them. In everyday life, we talk about relative space and time and relative motion. But there also has to be this absolute space and time and absolute motion. So again, if anybody hasn't read it, go read Newton's Scholium on Space and Time. It comes after definition 8 in the Principia, and you can just read it. It's like, it's absolutely clear. Newton, like Einstein, like Bell, very clear thinker, very clear conceptual thinker. He understands what his physics needs, and he gives you arguments for why you need it. So Leibniz, again, you just set them up. Newton says, even without any material bodies, space and time exist, absolute space and time exist. They support the notion of absolute motion. Leibniz says, no, space and time are just ways of talking about relative positions of bodies. Take away the bodies, there's nothing. Now, how does this get resolved? Not by a philosophical argument. It gets resolved by an experiment. Really, Newton is arguing directly against Descartes and Aristotle there. But Newton just says, again, if people don't know, do this experiment. And the nice thing about it is you can call it a thought experiment, but I do it in the class. I mean, it's an experiment. You can just do it. It's easy to do. The reason you'd think you don't have to do it is that you know how it's going to come out. But it's not a thought experiment in the way that, things you can't actually do. And you say, but if we were to, I mean, you can just do it, right? Just need a bucket. You need a bucket and some water and a rope. Yeah. And so Newton says, look, according to especially Descartes, and you can get this Descartes following on Aristotle, the motion that appears in physics when you say something is moving is again, like Leibniz, it's relative motion, but it's in particular the relative motion of a body to the surrounding body, to the body immediately next to it, right? So to take a standard example, Galileo talks about being in a ship that's on a calm sea, sailing on a calm sea, and doing experiments in the body of this ship. And he points out, and again, this is an observation. You can't tell from those experiments whether the ship is anchored in the harbor or sailing, as long as it's calm and it's not, and the ship's sailing straight. And all the phenomena will be the same. He talks about you've got butterflies flying around and water dripping down, and it'll all look the same. So are you moving or not? Suppose the ship is under sail, as it were, and you're down there and you say, are you moving or not? Now, one thing to say that you can say is, look, the relevant motion is just the relative motion of you to your immediate surroundings. And because if you're just sitting in your chair, you're not moving, right?
Right.
And so that's that was this idea that relative motion is physical motion. Now, Newton says, oh yeah, you think so? Because it's very important for Galileo, and Galileo says this, he doesn't make that much point of it, but he says it. He says that when that ship is under sail, it has to be on calm seas. It can't be tipping this way and that way, and you can't be turning the boat. If you do that, then you will notice, even though you're in the body of the ship and you can't look out, right? You can't track your relative motion with respect to anything outside you, but you'll notice inside. So Newton says, look, here's the experiment. Take a bucket of water, fill it up, tie it to a rope to the ceiling, and twist the rope very strongly. And imagine, so in the beginning, I've just got this bucket of water. And here's something you can see, because we're worried about what you can observe. The surface of the water is flat. Now, very quickly, spin the bucket and let it unwind. You imagine it unwinding with this. And Newton says, well, immediately after you do that, the bucket will start spinning relative to the water. Right now, you've got the water and the bucket is spinning. As I like to say, you can imagine yourself, you're an ant floating on a leaf inside the bucket. Now you notice that the handles of the bucket are doing this around you. So think of phase one is, at the beginning, the water and the bucket are at relative rest. So if you're the ant, you don't see this. And the surface of the water is flat. Let go of it. In phase two, now they're in relative motion, but the water's still flat. And then if you wait a while, eventually, and you can picture this in your head, as we would say, the water picks up the spin from the bucket, starts going around with the bucket. Eventually, now they're at relative rest. If you're the ant, you look up at the handle, it's not doing anything, but the water is now like this. The water is now concave. And then that's phase three. In phase four, the bucket, as it were, comes to rest in the room and the water's still doing this. So now there's relative motion again and the water is concave. And what Newton points out is, look, there's a clear physical effect here. Sometimes the water's flat and sometimes it's doing this. That's not because of the relative motion of the water in the bucket, because there's no correlation there. Sometimes when the water is at rest with respect to the bucket, the water, it's like this, and sometimes it's like this. Sometimes when it's spinning with respect to the bucket, it's like this, and it's like this. So the relative motion of the water to its container cannot give you the physical explanation of this effect. And what Descartes had been arguing is that it is that relative motion that is physical motion. And Newton said, no, it can't be right. You lose, right, Descartes? You lose. And he gives other arguments. And then you might say, well, maybe it's, so again, off the top of your head, you'd say, look, it's easy to understand. The water's flat when it's not spinning, and it's concave when it is spinning. And then you say, yeah, but spinning relative to what? If you think all motion is relative motion of bodies, spinning relative to what? It's not spinning relative to the bucket. And then you say, well, maybe it's spinning relative to the room. And now you could kind of imagine doing the same thing. Sit the bucket and spin the room around it, right? That won't change anything. It can't be, well, maybe relative to the surface of the earth. That can't be right, because there's obvious observable effects of the spinning of the earth itself, like the Coriolis forces that give rise to hurricanes going this way in the northern hemisphere and that way in the southern hemisphere, and the fact that the earth itself is oblate, right? It's the equator is sticking out. Why? Because the earth is spinning. Spinning relative to what? Right? As soon as you say that, you say there are physical effects of spinning. Spinning is a kind of motion. Well, if you think all motion is relative motion. Now, Newton, at the end of the scholium, takes this all the way to the end, to a real thought experiment. He says, suppose the universe only contained, the only matter in the entire universe was two spheres tied together by a cord. He said, if that system, and that's all the matter there is, if that system were rotating, were spinning around its center of mass, you'd have tension in the cord. And the faster it's spinning, the more tension. And you could even tell that it was spinning, even though there's no relative motion at all of the matter. You could tell it was spinning from the tension. And if you measured the tension, you could tell how fast it was spinning. So Newton has these really powerful arguments that you can't understand the motion that accounts for physical effects as merely the relative motion of matter. The key from Newton's perspective, if we look back on it, is that when Galileo gives his argument about the ship, his argument is, look, you can't tell by experiment whether the ship is anchored or moving, assuming it's moving smoothly. So that suggests, well, maybe there's no physical difference there. But you can tell whether the ship is spinning or not. And the difference is, of course, spinning is an acceleration. And the central equation of Newton's physics is F equals ma. So it's very different if you're talking about an accelerated or unaccelerated motion.
You know, everything you're saying is amazing, but this is a time where maybe a simple clarificatory question would help. Why is spinning acceleration? I'm not sure that would be clear to everyone. It's
sure. So there are two kinds of acceleration intuitively, the way you learn this initially. One is like when you're stopped at a stoplight and you put your foot on the gas and you feel pushed back in the car because, as you would say, you're going faster and faster. So an acceleration is a change in your velocity. And your velocity intuitively can change in two quite different ways. You can keep going in the same direction, but faster or slower. That's the kind of acceleration that pushes you forward and back in the car. Or you can keep the same speed, but change your direction. When you're spinning a uniform circular motion, your velocity, your speed isn't changing, as it were, but your velocity is, because the velocity includes the direction. And so this was Newton's key to coming up with his gravitational theory. I mean, this is the whole story about the apple and everything else. Newton says, wait, the moon, for example, is going around the Earth, right? It's orbiting, and the Earth is orbiting the sun. Those are accelerations because they're constantly changing their direction. By F equals ma, there's an a, this is an acceleration, there has to be a force. And for uniform circular motion, the force has to be a centripetal force. It has to be directed toward the center, right? Center seeking. So there must be a force that's keeping the moon in orbit. There must be a force that's keeping the Earth-Moon system in orbit around the sun. And it has to be a force directed toward the center of that motion. So for the moon, a force directed toward the center of the Earth. And for the Earth-Moon system, a force directed right at the sun. And then he makes various arguments as to the nature of that force, according to his own physics, that it has to be an inverse square force and so on. And then Newton does this wonderful thing. He says, okay, if I'm right, then we can figure out what would happen if we did the following thing. The moon's up there orbiting the Earth. Stop it, okay? Stop that orbital motion. And furthermore, pull the moon down right to the surface of the Earth here and drop it. So this is like Galileo. By what I've calculated, it would fall at the same speed as an apple. So this is like the ultimate version of Galileo's experiment with the heavy and the light object. The moon would fall at the same rate. That's the whole deal with the apple. He says, oh, I see. The very same force that causes the apple to fall is the force that's keeping the moon in orbit, and the force that's keeping the Earth-Moon system in orbit around the sun, and all the other planets in orbit around the sun. I mean, this was the point where Newton destroys the traditional distinction between terrestrial physics, the physics of things on Earth, and celestial physics. I mean, that's built into Aristotle. On Earth, things are made of earth, air, fire, and water, and their natural motion is either down or up. And in the heavens, they're made out of ether, and their natural motion is circular motion, right? So if you asked Aristotle, of course, he thought the sun was going around the Earth, but it's still kind of a circular motion. Why does it do that? Aristotle's answer is, oh, that's the nature of ether. That's just what ether does. It goes in uniform circular motions. And what Newton says is no. I mean, everything's natural motion, that is the motion it'll engage in if nothing is affecting it, is uniform linear motion. That's the second law. So it's puzzling that the Earth is orbiting the sun. It's puzzling that the moon is orbiting the Earth. We need a force for it to do that. And so he has the universal force of gravity, and he unifies celestial mechanics with terrestrial mechanics. Galileo had taken steps in that direction, but he didn't get there. And Newton finally gives you this theory. So all of this is absolutely central. The nature of space and time, the nature of motion, is central to Newton, and he argues very explicitly about it. And there were people like Descartes and then like Mach who just didn't like the idea that space and time had this independent existence. So they were trying to get that out of their physics, right? They were trying to remove it. As I say, Einstein thought at the end he would end up with a Machian theory. He kind of wanted a Machian theory. So he was not really on Newton's side here. The irony is that he ended up with a really non-Machian theory. So if you go into, for example, if you just take, the first question you should ask of any theory of space and time is the same one Newton asked. How do you explain that bucket, by the way? And in the special theory of relativity, even though you change from Newton's picture of space and time to a very new one, if you ask, yeah, but how do you explain the bucket? Same way. In that theory, there's also a fundamental absolute distinction between a spinning and a non-spinning body. And if you say, but what's the difference? The answer, you just have to bring in the space-time structure. It's not a difference in relative motions of material bodies. Now, I think Einstein understood for special relativity that was true, but he still had this hope that maybe eventually he could push even further and somehow get rid of it. But the normal way of understanding, the right way, the easy way to understand relativity is not to be confused and think that the theory of relativity is a relational theory. So that those two words are so close to each other that they get constantly confused. And people think, oh, in the theory of relativity, everything is relational or everything is relative, right? Nope. In the theory of relativity, so you imagine Newton's situation. I have these two spheres tied together by a cord, and the whole system is spinning. And there's tension in the cord because they're spinning. And it doesn't matter. There could be nothing else in the universe, material. The same is true in special relativity, and the same is true in general relativity. All of those are things that could happen according to all those theories. So Newton's argument that space and time have to have their own existence, their own reality, independently of matter, those arguments go through just as cleanly for special relativity and general relativity as they do for Newton. Those theories disagree about what the space-time structure is, but they agree that there is such a thing as space-time structure that's not a coded way of talking about relations between bodies. So again, now if we go all the way back to 1905, Einstein's worried about these relative motions that show up in electromagnetic theory and how the physical explanations depend on what's moving and what isn't, even where there's no spinning, even where there's no acceleration. The one we talked about of taking the magnet and sending it through the coil, there doesn't have to be any acceleration. That magnet can just kind of smoothly sail through the coil. You'll still create this electrical current. And what Einstein didn't like was that the account of that current was so different depending on whether it was the magnet at rest in the coil moving or the coil at rest in the magnet moving. So he comes up with this theory, and then Minkowski looks at it and says, oh, I see, really what you're telling us, Einstein, is that space and time, the structure of space and time themselves are very, very different than what Newton thought. And that's right. That's on target. Then you say, it's not that he's making space relative or anything like that. He's making space different, or really space and time, because in Newton's theory, you can cleanly separate the question, what is the structure of space, from what is the structure of time. Newton's space was just three-dimensional Euclidean space, infinite three-dimensional Euclidean space, and time was this succession of moments of time that come one after the other, and there's a certain distance amount of time that passes. So you would, the spatial structure you can specify independently, the temporal structure you can specify. What Minkowski realized is that one way of thinking about what Einstein was doing was taking the spatial structure and the temporal structure and kind of melding them together into a single thing that didn't have any distinction into the spatial part by itself and the temporal part by itself. And that's what we call Minkowski space-time. That's the space-time of special relativity. And it has just a different geometrical structure. And the difference between it and Newton's theory is not just subtraction. It's not like you start with Newton and you take some stuff away. You do take some things away from Newton and then you add things Newton didn't have. It's just a different structure. And then to say a theory is special relativistic is to say you can write down the fundamental dynamical equations of the theory just in terms of this space-time structure. So that's a very long answer. It tells you, but I'll repeat a couple things. The theory is not a relational theory of anything in terms of space and time. It postulates an absolute space and time. It has an absolute structure. It's a different structure. He wasn't worried about the Michelson-Morley experiment. He was worried about understanding Maxwellian electrodynamics. I mean, the real motivation, because there were only two existing precise physical theories to worry about at in the beginning of the 20th century. One was Maxwellian electrodynamics, which is the source of special relativity, and the other was Newtonian gravitational theory, which is the source of general relativity. So you can think of Einstein as going in two steps. First, I'm going to kind of get an account of electromagnetic theory that I'm happy with, and then I'm going to try to get an account of gravity that I'm happy with. And there's a 10-year gap between special relativity and general relativity where he's struggling to come up with a gravitational theory that is consistent with the theory of electromagnetism that he had written down in 1905. So if we get there, that's the sequence. But again, it's another change. You change your understanding of space-time structure and going from special to general relativity, although that change is in a certain way milder than the change from Newton to Minkowski. From Minkowski to general relativity is milder in certain ways, but it's also very radical in other ways. So, eventually maybe we'll get there. Okay.
As I told David yesterday, after his initial discussion of the problem of time zero, if I were willing to experiment with the microphones, which I'm not, I would have given him a thunderous round of applause, and I would do the same for you. That was really, really excellent. So thanks. And the next thing I'll say is I learned a new word a couple of days ago, hagiography. And I am interested in getting into some hagiography. So I'm really glad that you started off by talking about just how marvelous a mind Einstein was. Mm-hmm. It also didn't escape me that you compared him to Bell, who I know is another of your heroes. One thing that I just want to ask about quickly before we move on, because it's interesting since so much of our audience is probably philosophically inclined and have listened to a lot of our other conversations about philosophy where we've compared philosophy of physics with physics, philosophers with physicists. Mm-hmm. Something that you stressed about both of their thinking was conceptual clarity. Even though they weren't in philosophy departments, is it conceptual clarity that you identify with philosophical thinking that has such an important role in the work of the best physicists?
Yeah, I mean, two things, and they're both things you learn in philosophy. One is to make clear conceptual distinctions because you always have kind of nearby ideas that are different. And if you're not careful and you just kind of slop around between them, you get into a mess. And the other is of course, the same, it's a slightly different thing, but sensitivity to what follows from what, right? Logical sensitivity to see, oh, yeah, this conclusion follows from these premises. No, that conclusion doesn't follow. There's some tacit premise in the argument that you're missing, right? So often, of course, what one needs to do is notice that from some stated premises, a certain conclusion that seems to follow doesn't really follow. The reason it seems to follow is that you're tacitly making yet another assumption. And sometimes you can dig that up and put it in front of your face and you say, wait a minute, but maybe that's wrong, right? Maybe I'm making a mistake in my inference here. So I think both conceptual clarity and, if you will, logical clarity. But you can't do anything well without them. You certainly can't do anything well where the subject matter is complicated, because you'll just get into a mess. And yeah, I would say, and as with Newton, again, if just read Newton's Scholium on space and time. He's doing what we would call conceptual clarification at a certain point. He says, look, when we talk about space, time, and motion, there are two things we talk about. There's common, he has three words for it, right? Common notion and so on, these ones that are tied to our experiences. Like when I say, I'm not moving relative to you, or I don't see any motion. That is relative motion, right? That what I see, the fact that you don't look to be moving to me right now is because we're not moving with respect to each other. Even though in some sense you might say we're both moving as the earth rotates and blah, 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 right? And Newton says, look, there's common time, common space, common motion, which are used in everyday life. And then there's absolute true in mathematical time, absolute true in mathematical space, absolute true in mathematical motion. That's what physics is about. You can't do physics in terms of the common notions. And he's very clear about that. And why in everyday life it's kind of okay to use the common notions. But if you're doing physics, you have to use the sharp mathematical notions. And he makes that distinction, and then he gives this argument about why you have to make the distinction and so on. That you couldn't create Newtonian mechanics without being that clear. Einstein was trying to get that clear about electromagnetic theory in 1905. He again, in thinking about atoms, he said, let's take it seriously, right? I mean, people could be instrumentalists and say, oh, we postulate there are atoms, but that doesn't really mean there are atoms. It just means if you calculate or do something. And Einstein said, well, what if there really are atoms? What would we see? And this is coming off of Boltzmann and a whole bunch of stuff. The atom is, I mean, it was still questionable whether matter had an atomic structure. And Einstein thinks it through and he says, well, if there really are atoms, that would explain Brownian motion. That would explain why when I look at a little mote of dust, it jiggles around, right, in this random looking way. Why? Because it's being hit by these invisible gas particles. And looking at the nature of the jiggles, I can figure out how many there are, right? I can actually figure out empirically, right? This is, again, let's take that seriously and see what follows. Now, the thing that happens is Einstein, of course, wanted to have that kind of clarity about quantum theory once it got going, and he never got it. He was never satisfied with quantum theory because he didn't have what he thought to be a clear physical account of even what the theory was saying, what it was postulating. And the response to that, as we know, was shut up and calculate. I've given you, I'll tell you how to calculate and make the predictions. I mean, maybe this would help. You could imagine Einstein, I mean, we can play this little game. Einstein goes to his physics teacher with this electromagnetic problem. He says, look, physics teacher, if I hold the coil and move the magnet, I get this current. If I hold the magnet and move the coil, I get the same current. How do I, what's the difference? Why is it so different? That teacher could have said to young Einstein, Einstein, shut up and calculate, right?
Yeah.
Use Maxwell's equations. Yeah, you'll use them differently in the two cases. You'll get the right result both times. Shut up. Stop worrying about what's really going on. And then we would have never had relativity. We have it because he wouldn't shut up, because he was trying to think it through, trying to understand it. Yeah, I think that is absolutely the mark of great physics, is to try to get clear about really what you're postulating and how it works. And having some equations that you can grind numbers out of that happen to be correct in terms of their predictions, that's not what physics should be about. Physics should be about understanding, comprehension, intelligibility, things like that. And that requires conceptual clarity, it requires clarity in argumentation, all of the things that make for a good philosopher.
That was great. I'm glad that I asked that question. And to move on from here, I think that what you did in that first hour was marvelously intellectually motivate what was behind the theory of special relativity. And I really appreciate how far back we went in the history. One of the things that I found most fascinating watching and listening was going through the bucket experiment. For that reason, because of how intuitively, or how it pumps our intuitions, to how that might be how Dan Dennett would put it. I think it would be really nice to go through a thought experiment concerning special relativity to do the same thing for our listeners.
Right. So what happens in so Newton has argued, and just to write down F equals ma as your fundamental equation, there has to be a fact about what a is, right? There has to be a fact about accelerations. And according to Newton, if you put a force on an object, it'll accelerate. If it's a constant force, it'll keep accelerating, go faster and faster and faster. Imagine we do this straight acceleration, linear acceleration. No limit to how fast it can go. That's just a consequence of Newtonian theory. Now, in relativity, what we know is there's a sense in which the speed of light or the behavior of light or something like that, although it's not really light, this is in the space-time structure, is a kind of limit. So we could just say in terms of an experiment, suppose I take a charged particle and I start accelerating it by putting it in an electric field, like in the Stanford Linear Accelerator Center, right? They had a 2-mile-long tube. You put it on an electric field, you put a charged particle, zip, it goes down. And then you would notice that, no, I can't make it keep going faster and faster and faster, right? There's, as it goes faster, it takes more and more energy to begin with to make it go any faster at all. I can always, if I'm kind of doing a drag race between two particles, I can always make it go a little bit faster, but it gets harder and harder and harder and harder, unlike what Newton would say. He would say, add the force and you'll increase the acceleration. So that was a question, right? Why is it that there's a limit, just a limit in the lab, about how fast particles can go? And there was another, it's not as hard a question to ask, why does light always go, quote, at the same speed? What do I mean by that? Again, just think of doing a drag race, right? I have two people with flashlights, and they both press their buttons next to each other at the same time, and someone far away, do they see the light always? Does the light get to them together? If it did, then in a way, those two light beams were traveling side by side. Now, you might think, if this were, this is often an example you can use. Suppose you had two people with literally guns, right? Rifles. Side by side, they're both, I'm not going to shoot at you, both shooting at some wall over there, right? Identical rifles. They pull their triggers at the same moment. If they're just standing next to each other side by side, the bullets hit together. Now, suppose this one's, as it were, moving on a movable platform, is moving toward the wall. But again, when they're right next to each other, they both pull their triggers. The one moving toward the wall, his bullet will get there faster, right? It'll be the first one there. And if he's moving the other direction, if he's moving fast enough, the bullet will just fall straight down. If he's moving backward at the speed of the bullet comes out relative to the muzzle, even though they're next to each other, his bullet will just fall straight down. Does light work like that? No. You replace these guns with flashlights. And even if this one's going really fast that way, when they push here, the light still gets there at the same time. Now, there is a difference between the light. They'll have different colors. They'll be what's called red shifted or blue shifted. So the spectrum of color will change, but the time, right, they'll hit the wall together. So there's a kind of, I mean, that is a phenomenon one can describe as the constancy of the speed of light. That is, how fast light goes, or to be more precise, the trajectory of light through space and time is independent of the state of motion of the source. That's not true for bullets. So light is clearly behaving differently than, say, bullets, archetypical particles. Doesn't seem to really be a particle. Furthermore, what you're telling me is that if I release some light at a certain point, where it's going to go, that's determined not by the state of motion of the source. It's determined by what? It's determined by the structure of space and time itself. Somehow space, if you will, space-time is telling the light where to go. How does it do that? It needs some structure to do that. So in special relativity, this is part of putting in something Newton didn't have. There's a part of the structure of space-time that's called the light cone structure, or the conformal structure. And essentially, the hypothesis is that if you're in a vacuum, so you're not being messed up by some medium, right? The light's not going through water or something like that. If you're in a vacuum and you aim some light in some direction, where it will go is determined just by the light cone structure. So that's, and that is, again, without there being anything like a medium. There's no material medium, because you're saying this will happen in a vacuum. You'll say, and by a vacuum you mean there's nothing material around. So if you ask, how does the light know where to go? The answer is, it knows where to go just because space-time itself is telling it where to go, if you will. As we said, if there's no medium like air, sound can't travel through space, right? If you ask, how does sound know where to go? The answer is it's the air that, as it were, is determining the state of the air that's determining how the sound waves propagate. But light manages to go through space in what we otherwise call a vacuum. So the determining feature is the space-time geometry itself. And that is very different than Newton. That light cone structure puts a limit on how fast you can make particles go. And there's no such limit in Newton. So I'm not sure if that exactly, helps. I mean, we're at the point where to really understand the space-time structure postulated by special relativity, you got to get a bit into the geometry and the math if you want to be precise about it. There are some intuitive pictures you can have in your head that are very helpful. And one that is very helpful is one I'm sure everybody who's interested in this have seen pictures of light cones, right? So on the page, you have all these points, and then for each point, there's a double cone. And the cone point is this event. It has a future light cone and a past light cone. And you might say, well, what are those things? So imagine this cone point, that's an event. Imagine it's a light bulb going off. And in your mind, think, well, what happens when a light bulb goes off? Oh, a sphere of light shoots out in all directions and gets bigger and bigger and bigger. Now, that's three-dimensional, but we're now talking about space-time. There's an extra dimension, so we usually cut out one dimension. So imagine I'm a two-dimensional flatland creature, and I set off a light bulb. I get an expanding circle of light going out in all directions. Now, think about how that looks if I now have time going up in this direction on my diagram, and I set off my flash bulb here. I get an expanding circle. Looks like a cone. That's the light cone. That's the future light cone. And the past light cone is telling me all the light that arrives here. How did it get in? It's coming in along the past light cone. So what you need is an intrinsic space-time structure that determines what these cones are. And that's what special relativity has that Newton doesn't have. There's nothing in Newtonian space-time that corresponds to a light cone. What there is in Newtonian space-time is absolute simultaneity. So if you, again, can picture this in your head, in Newton's world, if I snap my fingers, that's an event. You can perfectly well ask, what else was going on in the entire universe at that moment? And so there's a kind of instantaneous snapshot of the entire universe. And then if I snap it again, a new snapshot, a new snapshot. You pile up these leaves, or these planes, as it were, of absolute simultaneity. That's part of Newton's structure. In special relativity, you get rid of absolute simultaneity. So again, this is, people often say, in relativity, simultaneity is relative, but it's not. It's non-existent. There is no such thing as simultaneity physically. There's no such relation. So you've gotten rid of these slices, which we call a foliation, fancy name, but you've replaced them with these light cones. But the interesting thing about the light cones is that whereas the slices, all the points on the slice are equally associated with that one slice, every light cone is only associated with a single event, the cone point, right? So I've got this double cone. That's associated with this event in space-time. And for this event in space-time, it's a different double cone. And for this event, it's a different double cone. So these are just very different structures. To understand relativity is to understand, first, what is the space-time geometry that's being postulated? And secondly, how do you write down the physics in terms of it? What physical consequences does it have? Once you've got these cones, we've already seen one consequence. I can tell you where light's going to go without talking about any medium at all, right? If I point the flashlight this way, it's going to go off along this part of the cone. If I point it that way, it's going to go along that part of the cone in a vacuum. Newton wouldn't have anything in his theory that would tell me anything like that. So now we can start talking. Now we can talk about, the twins, so-called twins paradox, or whatever you like. The main thing is to understand that these are physical phenomena, and the goal is to understand those phenomena in terms of this new space-time geometry. But I'm not sure exactly, where you, we've already seen that you can have a principle like nothing goes faster than light, which for Newton would say, what? He's thinking of, Newton thought of light as particles. He had a corpuscular theory. And if you ask Newton, okay, here's a light particle going along, could some other kind of particle go faster than it? He'd say, yeah, put enough force on it, right? Put enough force on it, you can get it to go faster. Why not?
I think I am very glad that you mentioned, a few minutes ago, let's just say, that to really understand this, you need to go deep into understanding the geometry of space-time. There are two reasons I'm really glad that you said this. One is that it is a reminder to me and to our listeners that you're one of the world experts on this subject, and why that's important for me to know is I want you to know that you should lead this the way that you think is most useful for us to understand special relativity. The second reason is that it's important for us to know that just in a podcast, we're not going to understand everything about special relativity, but what you've demonstrated is that we can still elucidate obscurities and confusions in broad strokes. That being said, something that I think would be really interesting to talk about, because we've just been discussing the speed of light, is that, assuming I'm correct, in the theory of special relativity, nothing is supposed to have a speed.
Right.
And yet, the speed of light is constant in a vacuum. And then furthermore, nothing is supposed to move faster than the speed of light.
Right.
I think this is a source of a lot of confusion.
Sure is. Absolutely. And for those of you playing at home, let me add to this. Physicists get really confused about this stuff. In my book, I talk when Richard Feynman tries to explain the twins paradox in his famous lectures, he gets it wrong. Just gets it wrong.
Wow.
He's a smart guy, and he was a guy also who always wanted a clear, concrete picture in his head about what was going on. He's wrong about it. And I'm not saying that. I know it's been verified from real experts who read my book said, yeah, you're right, he does it wrong. I mean, Sean Carroll, when he read my book, said, oh my God, I explained that wrong in my book. I have to go change that. I mean, so this is tricky. I mean, in a way, it's tricky stuff, right? So don't feel bad. But yeah, that's a nice conceptual thing. You say, wait, first of all, are there absolute speeds at all or only relative speeds? And Newton argued, no, there have to be absolute speeds. There have to be absolute velocities. Why? Because they have physical effects. And if you talk about, I mean, another argument Newton gives is, suppose you said there are only relative velocities. Well, right now, we have all kinds of relative velocities, right? My relative velocity with respect to you is essentially 0. But my relative velocity with respect to the sun isn't at all, because I'm on the Earth and the Earth is rotating and orbiting and we're going at tremendous speeds. So you say, but which of these relative velocities is the physically relevant one? They can't all be physically relevant, right? So Newton thought the only way out of this was to have absolute velocities. You couldn't directly observe them, and he talks about that in the Scholium. He says you can't see them, but you can kind of infer you can put constraints on them. And when we get to relativity, they're gone. There are no absolute velocities. So if you ask me right now, how fast are we moving? The answer is that's not a good question, right? There's the space-time structure doesn't have the right structure to give an answer to that question. And then you say, but wait, if nothing has a speed, if nothing has a velocity, if nothing has a speed, what do you mean the speed of light is constant? How can the speed of light be constant if there are no speeds? How can you say nothing can go faster than light if there are no speeds? So let's answer both of those questions. They're slightly different. When you say the speed of light is constant, you're saying what I just said, namely, from a certain point, release light in a certain direction, and let the source be doing whatever you want. You can be moving the source or spinning the source or whatever you like. But at this moment, have these two flashlights send out beams in the same direction in a vacuum. Those will stay neck and neck, right? If you put a wall, if you put a screen anywhere, both of those will hit the screen together. So you can't make one beam of light outrun another beam of light in a vacuum, in that sense. Notice I could say that without attributing a speed to any of them. I just say if you press the buttons together, send the light rays out together, they hit the wall together. So saying the speed of light is constant in a vacuum is just another way of saying that the trajectory of light through space-time is completely determined just by the space-time structure in a vacuum, right? Because there's nothing else to do it. So that's part one. Second question, but then what do you mean nothing can go faster than light? Well, again, in your head, you imagine this light cone. So I have an event here. I have this light cone that you can just picture in your head as a cone. That's where if I sent out light in all directions, it would go out along that cone. To say that a massive particle can't go faster than light is to say it can't start here and then go outside the cone. Its trajectory always has to, as we say, thread the light cones. So you imagine at every point there's this light cone. The trajectory of a particle is always, as it were, headed upward in the way we normally draw these. No more than you can't go more than a 45-degree angle because that would take you outside the cone. The cone's at a 45-degree angle. So you say the trajectories of particles are confined to stay within these cones. That says that the particle can't go faster than light. In exactly the same way, right? If I press a button and send light out in that direction in a vacuum, and then on the other side in this drag race, I have a particle, right, an electron, and I have some fancy accelerator, I don't care how you build the accelerator, the light will always get there first. So that makes sense out of saying nothing goes faster than light without mentioning a speed. I never had to mention a speed. I just, if you think of this kind of geometrically, I've got this cone, and I'm saying, all right, if you're going to draw the trajectory of a light particle, it can't do this. It can't, as it were, bend off and go through the cone. If it starts out here, its future always remains within the future light cone. Its past was always in the past light cone at every point. So that's the exact content of that.
Speaking of hagiography, I am not sure I can think of anybody who gets more saint treatment than Richard Feynman in the last 100 years of physics. Even Einstein, maybe. I mean, Einstein, I think, gets criticized a bit more than I hear Feynman getting criticized. The reason I think that that's interesting is even saints make mistakes.
Sure.
And I'm wondering, I think this might be interesting for our listeners and watchers so they can be on the lookout for this. What was the mistake that he and some others have made in trying to explain this?
Sure. So this was about explaining the so-called twins paradox.
Okay, well,
so
then
we can talk a little bit about that, and then I can explain the mistake he made, if you like.
Oh, absolutely. Yeah. What I was going to say after you responded to this was that I'm hesitant to call anything we've been discussing vegetables because it's all extraordinarily fascinating. But I think of things like the twins paradox, time travel as dessert. So maybe I guess we'll just skip some vegetables and go straight to the dessert and then talk about.
No, the twins paradox is, you have to understand how that phenomenon is explained to understand relativity at all. That's not an extra add-on. If you can't correctly account for that phenomenon, you don't understand the theory. So again, it helps to have a board, but if people can imagine, again, in your mind, imagine this structure, and you've got these light cones, and you have trajectories of particles that have to stay within the light cones. Okay? So you imagine all these different curves, continuous curves, but they can never go more than 45 degrees. Now, there is a fundamental quantity, the most important quantity in relativity, both special and general, that you associate with these trajectories. That according to the theory, this is a real objective quantity. It's just there in space-time, associated with these trajectories. It's called the proper time. You can think of it as a kind of measure of the length of these trajectories. So if I start here and start drawing one of these curves, there'll be a proper time length from here to here, and then if I draw a little further, it'll be more and more and more. I mean, as I go up the proper time, the length of it gets longer. That quantity doesn't care about coordinate systems. It doesn't care about reference frames, whatever those are, any more than if I had a piece of paper and I'm drawing a line on it, that line has a length, okay? It doesn't matter if I put coordinates on it or anything like that. It just has a length. That's part of its fundamentals, the fundamental geometry. So for these curves that stay within the light cones, this fundamental length is measured by a thing called proper time. And it's objective as anything there can be. And now, fundamental postulate, that's what clocks measure. If you want to know why does a clock read what it reads, if I set it to 0 here, and then it does something, right? In space-time, I can send it off on a rocket, I can spin it around, I can do whatever I want. It's following this trajectory through space-time, and its hands are moving or whatever. And you say, but why did the hands move that much from here to here? Answer, what an ideal clock measures is the proper time along its path. And if you can follow that much, you say, what do clocks measure? Clocks measure proper time. Then I can give you an analogy that completely explains the twins paradox, why it's not a paradox. You say, look, here's an analogy. It's going to be a really good one. In a car, we have an odometer. What does an odometer measure? Odometer measures, in some sense, the length of the path that the car took, right? If we set the odometer to 0, and later it reads some larger number, and the numbers will always go up. What's it measuring? It's measuring the length of the path it took from where I started to here. So I take two cars, identical makes, set their odometers to 0, sitting side by side. And then a few hours later, the cars are back together, side by side, and I look at the odometers. You say, wait, this one has more This one's higher than that one. And you say, yeah, what's the problem here? This one, the one with less took the highway, shorter route. The one with more took a scenic route, longer path. The odometers are just measuring these paths. They start out together, they end up different because they took different paths. That's not a paradox, right? Now, just apply that to proper time. Clocks measure proper time. They're measuring the lengths along these paths. I start out with 2 clocks side by side. I synchronize them. The 2 twins now, we've got, twin A and B. One of them, for example, just hangs out on Earth, so their trajectory through space-time might be this, or this, whatever it's doing. The other one gets into a rocket, takes a very different trajectory through space-time. It kind of goes way over here and comes back and blah, blah, blah. They get back together. Their clocks have different readings. That's not a shock. They took different paths through space-time. The paths had different lengths. The only thing that should shock you about that, should shock your intuitions, is that in the case of Euclidean geometry, which is the analogy I'm trying to give you to the odometers, if I had 2 paths in Euclidean space and one did sort of direct this here and the other one went the scenic route would be longer. It gets flipped over in relativity. The as it were, direct route, the straight route is the longest one, It's the longest one. And the one that does this will be shorter. That is, this twin will be older than this twin. That's kind of funny, and you can sort of see all of that arises in a very natural way, because one way to get at the geometry of special relativity is to take Euclidean geometry that we're all familiar with, where you've got the distance is the square root of x squared plus y squared plus z squared, this kind of thing that people are familiar with. And you just take a bunch of those pluses and turn them into minuses. Not all of them, but you leave one plus and the other's minus. So the distance is the square root of the difference in t squared minus the difference in x squared minus it. So you kind of flip a plus to a minus, and that takes paths of minimal length to paths of maximal length. There's kind of very systematic mapping. It's an inversion in a way between the geometry, Minkowski geometry, and Euclidean geometry. But once you kind of flip that over in your head, again, conceptually, I haven't given you any equations or anything, but just conceptually you say, what clocks are measuring are the lengths of these lines. If I start out with 2 clocks together and they get back together later, I can compare them side by side. The one that has run off more time is the one that took the longer path. And then all you need to know is that the longest path is unaccelerated. So if somebody's been just sitting there unaccelerated, they've taken the longest path. They should have clicked off the most time. That's why the stay-at-home twin in the normal twins example is older, right? The twin that goes out and comes back and it has taken this long route around, this other route around is actually a shorter route around. So that's the correct explanation. Now, what does Feynman do wrong? Feynman says, oh, there's this puzzle. Here's the puzzle about the twins paradox. And I'm going to state what he says the puzzle is, and you'll see immediately he was wrong in the statement, and then he's wrong in the resolution. So he says, somebody's going to say, but this is weird. I have these 2 twins. One's on Earth, the other is in a rocket, goes out, comes back, is younger. Then somebody says, but wait, the relative motions of the 2, that's symmetric. If A is moving relative to B, then just as much B is moving relative to A, right? Relative motions are, as it were, necessarily symmetric. So if everything is explained by relative motion, how could one end up older than the other? Why isn't it a perfectly symmetric situation? That's the puzzle as Feynman puts it. To which the answer is, relativity doesn't run on relative motion. You've already made a mistake. Right? Your puzzle is based on a mistake. Your puzzle is based on the thought that the only real physical quantities in relativity are relational quantities between bodies. They're not. This, again, this is true independently, even if there's only one clock in the universe. So there are no other clocks or no other anythings. It's going to travel on a trajectory through space-time, and its ticking, if it's a well-made clock, will reflect the length of that path, even if there are no other paths. So Feynman sets it up wrong. He sets it up, well, what is the physical difference between twin A and twin B, such that twin B ends up younger than twin A? And then his resolution is wrong. He says, oh, the difference is that twin B is accelerated and twin A is unaccelerated. And that's wrong too, because you can just set up situations where the more accelerated twin has the longer amount of time or the shorter amount of time or anything you want. There's really no fundamental distinction. There's no fundamental connection in the physics between the amount of acceleration and the readings of the clocks. And you can just show that. I mean, if anybody's interested in my book on space and time, it's very easy to see in these diagrams. Acceleration, I mean, here's the conceptual point. Acceleration has to do with how straight or bent one of these trajectories is. But clocks don't care how straight or bent they are, any more than your odometer cares how much you're turning the wheel, right? What an odometer measures is length. And length is a different quantity than bentness. Acceleration corresponds to bentness. Proper time corresponds to length. So Feynman thinks he's going to solve this problem, which is ill-stated at the beginning, and then to solve it, he mentions acceleration, which is the wrong solution anyway. I mean, it just doesn't work. Even technically, it doesn't work. The right thing to say is, no, it's not a theory where everything is relative. It's a theory where there is an absolute space-time structure, and what clocks read depends upon the trajectory of the nature of a trajectory through space-time given that structure. If you don't understand that, it's hopeless. Now, the irony is, if maybe we'll do another one on general relativity, Feynman gives a beautiful example, concrete example in general relativity that shows he understands that theory right on, right? And if we get there, it's a wonderful example. It's a puzzle, and I'm sure you're familiar with this. It's a puzzle that, if you think about it one way, it sounds very complicated. And to solve it, you need to do a kind of complicated calculation. But if you think about it another way, it's trivial and you can answer it like that, right? It's one of those cases where, yeah, shut up and calculate will get you there. But if you've got to get the answer by doing the calculation, you didn't understand the problem. Because just if you plug in the fundamental concepts, the answer immediately appears. So, and that's why I think that's part of what people loved about Feynman. He did care about this. He did care about having not equations and just, oh, here's some equations, now learn some math. Here's how to think about what's going on. He always wanted a concrete picture in his head, as it were, that he could think about before he did the calculations. He understood that the calculations aren't the key to understanding. You have to understand what you're calculating and why. And sometimes when you do that, you don't even have to do the calculation. It's just he made some mistakes, right? And it's not surprising. He made the same mistakes that everybody made about relativity, thinking it's a relational theory, thinking that, Minkowski space-time is just as absolute and non-relational as Newtonian absolute space and time. They just have different structures. They have different geometries. But in terms of, is one more absolute than the other? No, they're on the same plane. They're just different geometrically.
I'm really glad that we went through all of that. I think that the thought experiments really help get things into people's heads in a way that math, in a way that going through the concepts, even though they're necessary, they just don't always do. I have a few more questions, a couple of which are probably dessert, a couple of which are probably pretty vital. One of the things that I wanted to ask you about, though, because this is something that's on everybody's mind, even if it's not something that's vital to the work of physicists, is just what impact special relativity has on our conceptions or the possibility of time travel, either forward or backward, and whether or not time traveling forward and backward makes sense.
Yeah. So again, I'm going to say what I think is true. I don't think Einstein ever questioned there was a fundamental direction of time, ever. It never even occurred to him, any more than it ever occurred to Newton. Time, unlike space, is an asymmetric thing. There's a before, later, and we even show that when I talk about these light cones. They have two lobes, and everybody says, this is the future light cone, that's the past light cone. And you say, but isn't it symmetric if I flip it over? You say, yeah, but time itself is going, and there are conventions about this where you always draw them so that the future is to the top of the diagram. So or if we add a time coordinate, we always set up the time coordinate so it gets larger as you go to the future. As I say, we always do that, except when we're sending off rockets. Then we count down, right? Then as time goes forward, the number goes 10, 9, 8, right? Just a convention. But it's such a embedded convention that the direction of time is easy to read off these things without even thinking about it. So there's nothing that suggests, I would say, zero, that there isn't a direction of time. I don't think there's anything in physics ever that has suggested there isn't a direction of time. Time travel to the future, I mean, one thing you can mean is just, from where I am now, can I get to later points? The answer is, yeah, I hope so. I mean, I'm doing it all the time. Here we are. Time's going on. We're constantly arriving at later points in the future, right? to the future. So time travel to the future is not only easy, it's unavoidable. I mean, you can't stop it.
Yeah, I've been experiencing it for quite some time.
Yeah, exactly. And you're going to, no matter what you do. Now, there's the question, okay, but how much time passes? Because we just talked about in relativity, clocks are measuring proper time. And you can ask how much time is run off on this clock. So in the twins paradox, as it were, the twins start out together, and they're supposed to be identical twins, so they're biologically the same in everything when they start out. When they get back together, they're biologically different. One has gray hair, the other doesn't. One has wrinkles, the other doesn't. One has had subjectively 10 birthdays and all the stuff that happens in 10 years. The other has had only 6 birthdays and all the stuff that only happens in 6 years. Why? Because this path is longer than that path, and what time is the length along those paths. So if you wanted to get very, very, very far into the future from now and still be alive, one way you could do it, sort of, if we abstract from how getting killed by the process, is get in a rocket that goes way out and comes way back, just like in the twins thing. Your identical twin is long dead by the time you get back. You get back to Earth in the 30th century or whatever and see what's happened. And according to relativity, of course, that's possible because there is a path that takes you from here now to there then that's relatively short. It's a path that goes way out and it does something that's very different than this path. The as it were direct path is longer, as we said. The straightest path is also the longest path. So I can take these non-straight paths, as it were, that will do that. If that's what you mean by time travel to the future, can I arrange it so that I will biologically be, say, only 5 years older than I am now, but the surroundings will be the Earth many centuries from now? Sure, in principle you can do it. Now, probably to practically do it with those numbers, the trip would kill you anyway. As a matter of fact. But anyway, we're not talking about
Just
that
to be
now.
explicit, why would it kill you anyway?
Because in special relativity, to do that, it is true you would have to accelerate a lot. And accelerate, G-forces, I mean, you get in a rocket, you put too many G-forces on it, kills you. Right? as I mentioned to you before, if it is your desire, when biologically you are 5 years older than you are now, to be in the environment of the Earth in the 30th century, I would recommend looking into cryonics and having somebody freeze you and see if you can just, go into biological stasis and they can thaw you out. And then, you could see what happens. I mean, to me, that would be much safer and more likely to work than trying to do it with relativistic effects. Can you go into the past? Nothing in special relativity suggests that starting from now and watching a clock go forward, you can ever, you could find yourself in the 30th century. You're not going to find yourself in the 12th century. Nope, can't do it. Nothing suggests you can do that in special relativity. In general relativity, it's a trickier situation. I think even properly understood, general relativity doesn't allow you to do that, and that was normally the way the theory was understood, but if we do general relativity, we can get into that. So this is, again, conceptual clarification. First of all, what do you mean by time travel? Right? Do you mean I want to be in the 30th century on Earth, biologically being only 5 years older than I am now? Do you mean, I saw you talking to someone else about this, and you said you were confused. Do you mean if I follow my trajectory of through space-time, can it be discontinuous? Can it, as it were, go here, then suddenly, as it were, disappear, and then take up again here with, with nothing between them? And that raised this whole question, but is it you? I mean, that's this whole, is it really you, personal identity stuff? That's an entirely different question, right? That's a completely different question. I'm assuming for you to be you, your body has to, the parts of your body have to travel along continuous trajectories. And then the only question is, how long are those trajectories as measured in proper time? Then you can answer the question. If you think, I mean, to use, you were talking to, that was it. Think about these swamp men examples. They would suggest, if you believe that was personal identity, you can travel not only to the future or the past, but as far as, as far out in the universe as possible. All that has to happen is a bunch of particles have to come together in a Robinson-shaped configuration, and there you are. I think that's silly, right? I think it's silly to say that would be you. I think, if I die and some random particles far away happen to randomly assort themselves into a me-shaped configuration, cold comfort for me, I'm still dead.
Yeah, I could use some Robinsonian configured assistance.
Yeah.
That'd be very helpful.
Yeah, but they wouldn't be you, right? I mean, that's
True.
the point. They would be still numerically distinct, Robinson-shaped things.
Well, I'm glad that we talked about that too. Another concern, I guess it's not a concern, but a question I have. Physicists draw a very fundamental and important distinction between relativistic and non-relativistic quantum mechanics. Most of our discussions about quantum mechanics have concerned the earlier days, focusing on Bohr, as David referred to in our last conversation as the Church of Satan.
Yeah.
Or you referred to it as the Church of Satan. That was good. That was good. I like that. But my point is that with the exception of our discussions about Bohmian mechanics, pilot wave theory, we haven't talked that much about quantum field theory and more contemporary quantum mechanics.
Right.
So I'd like to ask how special relativity is important to understanding particles, fields, in quantum field theory.
Yeah, this is a very good question. Let me try and say some things briefly about it. There's this thing, so the original quantum mechanics was set in classical spacetime. So it had absolute simultaneity, just as Newton had. And you literally write down the equations with a time coordinate, which is global time moving on, right? That time coordinate, again, you imagine the spacetime, for Newton, the spacetime is, as we say, foliated or chopped up into successive global instants of time. And we coordinatize those with usually a number we call t, and as t goes forward, that's indicating successive leaves of this foliation like that. And you literally write down the equations with that t as a variable. So one thing that happens when you go to relativity is you get rid of that foliation. You can't do that. You can't write down the equations in terms of such a thing because according to the theory, it doesn't exist. You got to do something else. You might say, well, why don't I write down the equations in terms of proper time? You said there's this thing proper time. And you can do that for classical, for Maxwellian electrodynamics. That's why Maxwellian electrodynamics can be put in a completely relativistic form. And you can do it for the general theory of relativity, for gravity and the general theory of relativity. Essentially, the only time that comes in is proper time. You can't do it for quantum mechanics. That has to do with entanglement. That has to do with these features of quantum mechanics that are very non-classical, and they're kind of holistic and global and involve wave functions. You've talked to a lot of people about that. I mean, we can't, but that's why Schrödinger said entanglement is the feature of quantum mechanics that forces a divergence from classical lines of thought. There's no obvious way at all to go from non-relativistic quantum mechanics to a theory that doesn't somehow involve a foliation. But then you say, but what about relativistic quantum field theory? Well, relativistic quantum field theory is only, quote, relativistic in a thin sense, and it's not deeply relativistic. It never was. This again comes back to what makes a theory relativistic. Correct answer. Theory is relativistic if you can write down all the equations for it cleanly using only the relativistic space-time structure, which means no foliation, because there's no foliation in that structure. Nobody's ever done that with field theory, ever. Well, what did they do? Well, Dirac came along, and the Schrödinger equation is written in classical space-time. He came up with the Dirac equation, where you replace that with some relativistic-looking kind of stuff. But what you understand at this point from all your other interviews is that it's very unclear what the fundamental dynamics and ontology of quantum theory are. Are there collapses of the wave function? Are there not collapses of the wave function? Is that a physical thing? Is that not a physical thing? You have to settle all that. What's physical and what isn't, before you can even ask the question, can I articulate this physics using only relativistic structure?
And I cannot underscore enough how familiar I am with this at this point.
Yeah.
You're right.
Right. So people who say, oh, there's really can't be a problem reconciling relativity with quantum theory because there's, quote, relativistic quantum field theory. That's just wrong. There does not exist properly a relativistic. The nearest thing we have to a relativistic quantum theory is the relativistic flashy GRW collapse theory that Roderick Tumulka came up with. That's not a theory that pretty much any actual practicing physicist uses or is even familiar with. So if they think they're using something relativistic, they're just confused. They think when you say, if you ask, but why do you think your theory is relativistic? They'll say things like, oh, because you can't send signals faster than light. You say, so what? That doesn't show a theory is relativistic. I mean, the theory of relativity is not, the fundamentals of it are not articulated in terms of signaling. And in fact, it's almost as bad, not quite as bad, but almost as bad as trying to articulate a theory in terms of measurement. And you've been through all this with David, right? Measurement just isn't the right kind of concept to be sitting at the bottom of physics. Neither is signaling. There are no fundamental physical principles about signaling. There might be consequences of fundamental physical principles that constrain what you can do when you're signaling. But physics isn't written in the language of signaling. Relativity isn't written in the language of signaling. It's written in the language of geometry. So there is a lot to say about this, But the first thing to say is the standard story you'll get from physicists about quantum field theory being relativistic, it isn't, not in the relevant sense. Write the theory down cleanly from beginning to end using only relativistic space-time structure. See if you can do that. But first of all, you've got to have a clear articulated theory. And typically, when it comes to quantum mechanics, as you know, they don't. Then it's shut up and calculate.
I don't know if this is a question that you think would be appropriate for this conversation, but what I'm wondering is, I know that you are a very strong proponent of pilot wave theory of Bohmian mechanics. Something that I often hear about Bohmian mechanics is that it has a serious problem with special relativity. And I'm wondering if this is something that we can talk about at a pretty high level, just at a sky level view to make.
Yeah, it does.
Okay.
But that's not, I would say it's not a bug, it's a feature.
So what does this mean, though, that it has a problem? Can we flesh
It means
that
I
out?
can't write down those equations. So if I go and try and write down, say, take the non-relativistic version, which involves two equations, the Schrodinger equation, which is already a little puzzling because it governs the wave function, which is not a local thing in space-time at all. And then the guidance equation, which tells you, given the wave function, how the particles move, right? What their trajectories are. Now, you can't write down the guidance equation without using absolute simultaneity in the non-relativistic theory. I mean, the time order between distant experiments, and David has a nice example of this in his book. Alice and Bob are doing experiments in separate labs, very far away from each other. In a local theory, nothing that Alice does makes any difference to what Bob sees. Nothing Bob does makes any difference to what Alice sees. That's sort of the intuition of locality, the one that Einstein had. If you put them far enough away, they're causally isolated from each other. In pilot wave theory, they absolutely are not. In pilot wave theory, you first of all write down the equation with this absolute simultaneity. And sometimes if Alice does something, that will make a difference to what Bob sees, and it will depend on whether what she does before Bob does his experiment or after. So the absolute time order between these two distant experiments is physically important. It determines whether Bob's experiment comes out this way or that way. You can't get, this is the non-locality of the pilot wave theory is in your face in the equations. It's manifestly non-local. And that's why Einstein didn't like it, because Einstein didn't like action at a distance. He didn't like the non-locality. Einstein didn't understand, of course, Bell's result, that you can't get away from it. So Einstein spent the rest of his life trying to find a theory that was local. Only after he died did Bell prove you're out of luck. You're not going to find a local theory. So from my point of view, the correct moral of that is, sorry, relativity. It looks like we need something like absolute simultaneity back again. We need a foliation back again for reasons Einstein didn't understand. So when you say there's a problem, yeah, you can't write down that theory using only relativistic space-time structure. But I don't think that's a problem with Bohmian mechanics. I think that's an indication that that's a consequence of the world itself being non-local. And I know the world itself is non-local because I can do experiments that violate Bell's inequality. That's not interpretation. That's go in the lab, right? Go in the lab, do these experiments. Here's a constraint on local theories. That constraint is violated. Conclusion, the world is not local. Okay, now I somehow need to implement non-locality in my physics cleanly, conceptually cleanly, in the equations. The easiest way to do that is to put back in a preferred foliation. I'm not saying it's logically impossible to do it some other way. The easiest way to do it is to say, this is an indication that relativity isn't right. It's not a complete account of space-time structure for reasons Einstein couldn't have imagined. And, okay, we learned something, right? Bell proved something really, really, really important. And what you should do is try to take it on board. People are wedded to relativity in a completely irrational way because special relativity was developed to account for Maxwellian electrodynamics, which is a local theory. General relativity was developed to account for gravitational phenomena like Newton, which is a local theory. Neither of those theories could give you violations of Bell's inequality. What Einstein realized was that you don't need absolute simultaneity or you don't need a foliation to do that work. He's right. What Bell realized is that no local theory can do all the work. And at that point, you should say, okay, it looks like, yeah, there's a problem here. I can't write down pilot wave theory in a relativistic way. The problem's with relativity. The problem's not with pilot wave theory. And if you disagree, then you give me a clean version of your theory, a clean, conceptually clear version of your theory using only relativistic space-time structure. I dare you. Give it a shot, right? The physicists get away with this because, again, they're just fuzzy about what their theory is, right? They're using all these kind of half-baked rule of thumb principles that you can't reduce to clear physics. And so if the acid test is reduce your entire theory to a clear set of equations, a clear ontology. Don't use words like measurement, for God's sake. And then show me those equations, only use relativistic space-time structure. If you can do that, you got something. But it's hard. The only person I know who's ever done it is Roderick Tomolka. And I think if you look at the theory, it exists, but I don't think it looks like a convincing sort of way this is a judgment. It looks to me a little bit ad hoc or put together. It doesn't look like a natural theory to me. None of the collapse theories have looked natural to me. That's why you say I'm a proponent of pilot wave. It's more just feeling like collapsy dynamics doesn't, that seems implausible to me. I prefer a theory that doesn't have that feature.
I'm glad that you mentioned locality because that is something central to quantum mechanics and it's a huge puzzle. Something that I just want to ask about briefly is whether or not in quantum mechanics there are in fact things that move faster than the speed of light, or if they only appear to do so. And what I have in mind are maybe fields or causality in some sense.
Yeah, so there's a big difference between those two.
Oh, I know.
So if you have a local object, which means something that can be pegged to regions of space-time, it has a trajectory. And you can ask, does that trajectory ever go outside the light cones? Does it go faster than light? There are theoretical particles called tachyons, which would do that, right? Their trajectories would, as it were, be horizontal. There's no indication there's anything like that. There's no indication there is a locally definable thing that follows a trajectory and the trajectory goes outside the light cones. But then you asked about causation. But causation doesn't require that, right? I mean, if the theory tells me if I press a button here, a light will go on there. And regularly it does, and furthermore, I can press it at random, and I want to even signal to you, I send you a message in Morse code by pressing this button, and that light's going on and off. We might say, yeah, there's a causal connection there. And that might be at space-like separation. That might be, I press the button here, and the light goes on outside the future light cone. That would be superluminal causation. Every quantum theory has that. That's what it is to say you can only get this phenomena with a non-local theory. The locality is causal locality. The Bell's locality condition is a causal condition. And what he says is causation, as it were, has to go faster than light. But go faster than light is misleading because it's not like you can track something going from here to there. It's just this event caused that event at space-like separation. So that you need. Okay.
Tim, as you know, I am a big fan of you. I'm a big fan of David. I'm a big fan of Barry. And one thing that all three of you have in common, though you're at NYU, Columbia, Rutgers, three of the best philosophy programs in the world is that you're also all part of the John Bell Institute for the Foundations of Physics, which you incidentally started. I am a proud donor. I'm a proud supporter in some other ways. But for the last couple of minutes, I just wanted to hear, since we probably have new listeners every time that we talk, just what it is and why you started it and how people can help.
Yeah, okay. So I started it because I came to Rutgers originally. Barry was there. Barry was friends with David. I got to know David. Shelley Goldstein was in the math department there. I set up a thing for years and years and years where a bunch of us, including Ned Hall, got together every year up in Lake Placid to talk to each other because we needed to, because this is the only way you make progress. And you need to be able to talk to each other in a very unstructured way. It can't be, oh, for 15 minutes you're going to have a presentation, then 5 minutes discussion, another presentation. And we would just go into a room and say, okay, start talking and talk and talk and talk until we got tired of some topic, and then start another one for as long as it took. That's the only way to make progress. The John Bell Institute, my hope for it is to scale that up, to make it a more global thing, but an actual physical place where people can come who are interested in this, who have backgrounds in philosophy, who have backgrounds in math, who have backgrounds in physics. You need people from all of these disciplines interacting with each other in an open way without a lot of time constraints. That's what I want to create. I thought I had a place to do it, which have been raising money. You contributed to. There's still the fundraiser is up to find a permanent location. The permanent location I thought I had, that I put a bunch of money into to build a lecture room and so on, unfortunately, it's not going to work out. For various reasons. One is that the only nearby local restaurant closed. And so there was a logistical problem feeding people. It was kind of okay, we could do it with this restaurant, but so we're now looking for another location. I have various lines of possibility that I'm pursuing. I've been hoping that one becomes concrete enough for me to announce. Instead of doing it here, where I'd been trying to get it done, we're going to do it in this other place. There are like 4 different places that are floating around, and coalitions with other institutions that are floating around. Nothing's nailed down. At the moment, it's just things are slow, and I'm hoping eventually I'll be able to talk to people and get enough momentum behind this to say, here's the new plan. So that's where we are now. It's nice that the thing exists as a organization of people. My hope was to make it a physical place where during the summers people could come and talk to each other, or just hang out if they're working on things with other people who might want to hang out there in a nice location, which my preference is somewhere in Croatia on the coast. There are different places that are possibilities that are floating around. So I hope by the end of this last summer to know what the most likely thing was, but I don't yet. And so I'm still waiting on that.
Well, Tim, I sincerely hope that you do find this location. Hopefully, maybe it sounds like our next podcast won't be there, but hopefully one day we do one in person there. But I implore all of our listeners to check out the website and see if they can help in any way. But for now, this was absolutely excellent. It was wonderful to finally do one of these in person. So thanks again so much for joining me, especially at 8 a.m. on a Saturday.
Thanks for having me.